This video is sponsored by Unacademy, one of the largest learning platforms in India. Check out their Learn Competitive Programming by CodeChef subscription and use our coupon code simplesnippets to avail discount. More on this later in the video. Hey, what's going on guys, Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And as the title of the video suggests, today we are going to understand the entire working of delete node operation in a binary search tree. Now before we proceed, I'm guessing you guys already know what is a binary search tree, what are the properties, what are the pros and the different operations that we've already discussed in this DSA course. If not, if you have any confusion, please go check out those videos in this DSA course, in this DSA playlist. I'll drop the link in the video description. Also make sure you understand what is recursion and what is a recursive function because we are going to use that in this tutorial. If you don't know that, I have a separate video on that as well, link in the video description. And with that being said, let's get started. So this video is going to be a little lengthy, so make sure you watch this video till the end. I highly recommend that you keep your phones aside, keep it on silent, keep any distractions away and watch this video from start to end in one go with full concentration, and then I can assure you that this delete node operation in a binary search tree will be very clear. It's not a very straightforward operation like insertion or searching. So there are multiple scenarios and all, so we have to discuss that in detail. So keep that in mind. Now talking about delete node operation in this tutorial, we are going to see the working steps. We are going to take an example, this visual diagram. Then we are going to see the pseudocode and try run that pseudocode onto our visual diagram on this digital blackboard. And lastly, we will convert that pseudocode into a C++ program. So we will cover the practical side as well. So there's lots to cover. So without further ado, let's start with the delete node operation. So on the right hand side, you can see we have a binary search tree. This is the root node. And as the name suggests, when you're talking about delete node, we want to delete a node in this binary search tree. Now, as I mentioned, the deletion is not that straightforward, and that is because the process of deletion of a particular node depends upon where that node lies and does it have any children or not. So for example, you can see that N4, N5 and N6 are the leaf nodes, which means that they do not have any further children. They don't have any children at all, right? So deleting them is gonna be pretty straightforward. Similarly, a node with a single child like N2 can also be deleted with less complexity compared to a node which has two children. For example, you can say N1 and N3 have two children, right? N3 has N5 and N6 and N1 has N2 and N3. So deleting the node with two children has a different procedure, and that's where a little bit of complexity is added. So before we take a look at the algorithmic steps which are there on this left hand side, let's just say you want to delete a node with the value of 10. So you want to delete this node N4 with the value of 10. Let's try to make our own logic. Let's try to understand how we can delete this node. So this is a leaf node N4, which means that it does not have any further children, right? So of course you'll first start with the traversal from the root node N1 and you will compare the number 10, that is the value 10, with N1's value which is 30, and you'll see that okay, 10 is less than 30, so you'll go from N1 to N2, correct? Because this is a binary search tree, I hope you know that the binary search tree follows a strict rule, and that rule is that for every node, the left subtree will have lesser values or smaller values and the right subtree will have larger values, right? So this is a rule which is followed strictly in a binary search tree. We've already discussed that in previous videos. So since 10 is less than 30, we will traverse to N2, which is to the left side of N1. Again, you'll compare 10 with 18. Again, 10 is smaller than 18. So again, you'll go to the left of N2 and you'll arrive at N4. Now, when you arrive at N4, you'll get a match and then you can simply erase this entire node out. So this is the deletion process when it comes to deleting a leaf node. Now this looks pretty straightforward, right? Pretty plain and simple. You simply traverse to the leaf node and erase it out. And you can see our structure of the binary search tree is still intact. We are not having any broken links or something like that. And it looks pretty basic. Okay? Alright. Now let's say you want to delete a node which is having only one child. So you want to delete a node having value 18, which is in the N2 node. So again, you'll start with the root node. You'll compare 18 with 30. You'll traverse to the left because 18 is less than 30. You come to N2 and you find a match, and now you want to delete this node. So when you delete this node, what happens is you can see that now there is a broken link. You can see that N1 is not linked to N4 now. So when you do the deletion, you'll also have to take care of linking this n1's left address or left pointer to this n4 node. Okay? And only then you can say that you've done the deletion properly, because now you have a proper structure. So when you want to delete a node with a single child, you have to maintain that link also to that node's child, right? So there's that. So again, this is also understandable. Okay, so now let's delete a node which has two children. Let's say you want to delete a node with the value 30, and 30 is value inside n1 itself. So you'll start with traversal from n1 and you'll get a match at the very first beginning. And now you go ahead and delete n1. And now this is where a little bit of confusion and little bit of problem is started, because you can see that we don't have a root node, or we don't have a node, and now the entire binary tree or binary search tree is broken into two parts. So our structure is completely broken and we need some node to take this place. Correct? We just deleted n1 with the value 30. So some node or some node value from these nodes have to come at this place. Now we can't just simply pick out any number and put it over here. Why so? Because then the rule or the principle followed by binary search tree might not be maintained. So what do I mean by that? So let's say if I just simply randomly take n4 and bring n4 over here with the value of 10, okay, as the root node. So this is the new root node that I make, and then I remove this out. This is easy to delete, right? This is a leaf node, so easy to delete. And now I'll say that okay, so I've brought n4 over here as the new root node, and now the binary structure is maintained. But there is a problem. Is this a binary search tree now? That's the real question, because now you can see that n4's value 10 is smaller than n2's value 18. And remember, in a binary search tree, for a particular node, let's say that node is n4 now, what is the left subtree for n4? It is this. And what is the right subtree for n4? It is this. Correct? So for n4 with the value of 10, in the left subtree, the value should be smaller than n4. But over here the value is 18, which is greater than n4. So hence now you cannot say that this is a binary search tree. That rule has been violated, that rule has been not followed. So this is a binary tree, the structure is there, but this is not a binary search tree. And hence now this has completely broken our logic. And that is the reason why when you delete a node which has two children, we have to strategically pick a node in such a way that the rule of the binary search tree is maintained. For example, if I bring n5 over here, let me bring n5 over here. What is the value of n5? It is 42. And if I erase n5 now, and now if I see the binary tree, the structure is again brought back to its proper place. It is a proper binary tree. The links are not broken. We have a new root node, and it is also a binary search tree, because if you see the left subtree for n5, the values are 18 and 10, and 18 and 10 are less than 42. And if you see the right subtree, the values are 45 and 67, which are greater than 42. So this is the right subtree. So this means that the rule of binary search tree is still followed, and also that rule applies to every node. Okay, so for every node you have to check that rule. So for n2, the left subtree is n4 who has a value of 10, which is less than 18. For n3, the right subtree we have is 67, which is greater than 45, and we don't have a left subtree. So the rule is applicable to every node in the binary search tree. And now the rule is followed, and now you can say that this is still a valid binary search tree. Okay? Alright. So I just wanted to briefly discuss this delete node operation in a logical way, and just wanted to show you how the delete would happen. And we just developed a basic logic, basic understanding of the different cases and different scenarios when the delete node happens. Okay, so now with this understanding and basic logic of delete node operation in different scenarios, let's take a look at the delete node algorithm and try to apply that algorithm onto this example. So in this algorithm, we have two different scenarios. The first scenario is for a leaf node and a node with single child. So the algorithm that is necessary to delete a node, which is a leaf node or a node with a single child, is the same. So when you write a program, the code is going to be the same for deletion of a leaf node or a deletion of a node with single child. And the second scenario is when the node has two children. That is when, as I mentioned, the complexity increases, and we have to particularly select a node which satisfies the binary search tree rule. So we have some different set of rules for that. Okay. So right now let's first see the algorithm for a leaf node or a node with a single child. Okay. So let's first see the algorithm for a leaf node. Let's say you want to delete n4, so you want to delete a node with the value 10. So let's try to go step by step in this algorithm. Let's see the step 1. Now the step 1 says you have to traverse to the leaf node or the node with a single child to be deleted, and let's say it is called as n. So the node to be deleted has to have a value of 10. So you'll start the traversal from n1, you'll go to n2, you'll go to n4. I hope you know how the traversal goes. And now you'll get a match. So this is step 1. Let's call n4 as n. And now you'll go to step 2. Now in step 2 you'll say check if n has a left child. So over here, does n, that is n4, have any left or right child? No. So when it does not have any child, programmatically it will have null. Correct? When it has nothing, it will have null in the programming perspective. So you have to check if n has a left child, that is n of left. It does not. So the next step is, if it does not, then link the right child with the parent node of n. So this statement is saying if it does not, that is if it does not have a left child, that is if n4 does not have a left child, link the right child with the parent node of n. Who's the parent node of n4? It is n2. You can see n2 is the parent of n4. So what we have to do, we have to link the right child with the parent node of n. So the right child of n4 is again nothing, which means that it is null. So now we have to link this as the parent node of n4. Who's the parent node of n4? It is n2. So n2's left will now be linked to null. Okay. And now you can erase this node out because this condition got true. Now in case if n had a left child, then you have to check if n has a right child. And if it does have a right child, then it is a scenario with the node with 2 children. So that is a separate discussion. But if it does not have a right child, then we have to link the left child. Okay. So this step will only happen when the node has a left child. Okay. And that would mean that we are looking at a node with a single child. Okay. So right now we are not dealing with step 3. What we did is we basically linked n4's parent n2. So n2 had a left child of n4, but now n2's left child will point to null. And now we can easily erase this link to n4 and delete n4 out. Okay. So basically what we did is we made n2's left as null. You can see n2's left was n4, but we linked n2 to a null value now. So essentially you have deleted n4. Okay. So if things are a little confusing, now let's see how you can delete a node with one child. Okay, so now let's say you want to delete a node with the value 18, which is n2, and n2 is a node with a single child. So again, the same algorithm is going to be applicable. Step 1 says traverse to the node which is supposed to be deleted, and let's call it n. So you'll start from root node, you'll compare 18 to 30, 18 is less, so you'll go to n2, you'll get a match over here, and now you'll go to step 2. Now it is saying check if n has a left child. Now n2 has a left child which is n4, right? So if it has a left child, then you'll not go to this step, because this step is executed only when it does not have a left child, right? So you can see if it does not, then you do this. So step 2 will be excluded. Now you'll go to step 3. Now step 3 is saying if n has a left child, then check if n has a right child. Does n2, that is supposed to be deleted, have a right child? No. It would mean that in the right of n2 we have null. Correct? So now in the third step we are saying if it does not, link the left child with the parent node of n. What is the parent node of n2? n2's parent is n1. We have to link the left child of n2. What is the left child of n2? It is n4. We have to link n4 with the parent node of n, that is with the parent n1. Okay. So this linking has to be done. And when n1 is now linked with n4, you can simply erase out n2. Correct? And when you do that, this link is broken. This link is broken. But now n1 is still linked with n4. So you deleted a node with a single child and you still maintained the link between the parent node and the child node of that node to be deleted. Correct? Okay. So I hope you've got an understanding of the delete node operation or algorithm for a leaf node or a node with single child. And even if things are a little confusing, don't worry, after this we're going to see the pseudocode as well. So things will be very clear over there as well, because we're going to dry run that pseudocode onto our example. So now that you've understood the delete node algorithm for a leaf node or node with a single child, let's see the algorithm for node with 2 children. Okay. So let's say you want to delete a node with the value 30, and that is n1 itself, which is the root node. Now as we saw earlier, when you want to delete this node, there has to be some other node that will take this place, and that has to be strategically selected. When I say strategically, it means that we have to select a particular node in such a way that the rule of the binary search tree is still maintained. Correct? So let's see the steps for deletion of node with 2 children. So step number 1, traverse to the node with 2 children to be deleted. So you'll start with the root node and you'll get a match itself over here. So 30 is matching with 30. So now we want to delete n1. Okay. Alright. Now we have step 2a or 2b. So there are 2 ways in which we can select a node that will take its place. Okay. So the first way is find the smallest node n-min in the right subtree of n. Okay. So this is the node to be deleted. This is n. What is the right subtree of n1? It is this subtree. Correct? This is the right subtree. RST is for right subtree. And step 2a says that find the smallest node, that is the node with the smallest value, in the right subtree of n. So who is the smallest node or the node with the smallest value in the right subtree? You can see n5. n5 is 42. 42 is smaller than 45. 42 is obviously smaller than 67. So we find this node. Okay. Now we found this. Now since we are doing 2a, we don't have to do 2b. 2b is another way in which you can find a particular node to be replaced, and we'll talk about that in a minute. But now since 2a is done, let's move to step 3. In step 3 it says replace this node n-min, we are saying n-min, with the node to be deleted. So n5, the value of n5 will be copied in n1. So let's erase 30 and let's write 42 over here. So programmatically we are not going to delete this node. We are only going to copy the value of this node into the node to be deleted. Okay, so that's why I'm copying the value. This still stays n1 only. So that's why I replace this node. Replacing is done. And now step 4 says now delete n-min using the delete process again. So n5 was n-min, which is the minimum value in the right subtree. So now this step 4 is saying we have to delete this node. So now you can delete this node using the delete node operation again. So you can see a recursively delete node is called, and this time this is a leaf node, so the deletion process is gonna be for a leaf node. And when you delete this node, this 42 is erased, but basically what has happened is this 42 is copied in n1 now. And now if you still apply the binary search tree rule, you can see the right subtree values are 45 and 67, which are greater than 42. The left subtree values are 18 and 10, which are smaller than 42. So the rule is still maintained. So this is how you go about deletion of node with 2 children. Now as I mentioned, there is another way in which we can select a node to be replaced, and that is in 2b, where you say find the largest node in the left subtree. So first step is to traverse to the node to be deleted. Let's say you want to delete 30. You have to traverse to n1. This is supposed to be deleted. Then in step 2 you are saying find the largest node in the left subtree of n. So if this is n, the left subtree of n1 are these 2 nodes. Correct? In that we have to find the largest node, that is the node with the largest value. It is n2. So you have to select n2. And now step 3 and step 4 are gonna be the same. So replace this node that you just found out, which is the largest node in the left subtree, with the node to be deleted. So n2's value is gonna be copied in n1. So 18 is gonna be copied over here. And now you can delete n2, which is at step 4. So now delete that node using the delete process again. And when you delete a node with a single child, which is this n2 that we just deleted, we have to simply connect this link again, and then you are done with the delete process. And again, the rule of binary search tree is maintained for this newly transferred or newly deleted node. So now this is the left subtree for n1. n1 is having a value of 18. In the left subtree you have 10, so 10 is less than 18. For the right subtree we have 45, 42, 67. All of them are greater than 18. So the rule is still maintained. Okay, so this was the entire delete node algorithm in the form of steps and the two different scenarios for the delete node operation. So I hope you've got a basic understanding of how the delete node operation would look like, the algorithm at least. But ultimately we want to implement this algorithm, this delete node operation, in our binary search tree program in C++, right? So for that we need a little bit of pseudocode steps which look like part code, part English, so that we can easily convert them into C++ programming. So this is just plain English algorithmic steps, right? So now let's see the pseudocode for delete node operation. This video is brought to you by Unacademy. They have launched a competitive programming subscription with CodeChef, and this is an all-round solution for anyone and everyone who wants to be a pro in competitive programming space. Some of the special features include learning from the world's best programmers, ICPC World finalists, and software engineers working in the best product companies, interactive sessions where you can engage with your expert educators, structured courses with doubt solving by expert panel of teaching assistants and community members, teaching in both English and Hindi language, so language is not a barrier, and I personally find this very cool. And in addition to this, there are special free live lectures that you can attend to experience the subscription. Oh, and did I mention you get an extra 10% discount with our coupon code simplesnippets on your 6 and 12 month subscription, and get the first month course at flat 999 rupees with this coupon code. Go to the link in the video description and check out the competitive programming package. Okay, so as you can see on the left hand side we have this huge pseudocode. Don't worry, don't get intimidated, it's pretty basic. We will go step by step. And on the right hand side we again have the same binary search tree, but this time the representation, the diagram, is representing a particular node in the memory, in the computer memory. So over here this is going to be the root node with the name n1, and this hash 31 is nothing but the memory address at which this node is created. Of course this address is a fake address, it's not real, it's just for understanding purpose. The center one is the value of this node, so n1 has the value 30, and the left and right are nothing but pointers or addresses to the left and right child respectively. So over here n2 is created at hash 16 address, so hash 16 is stored as the left child address of n1, and so on and so forth. I'm guessing if you have watched any of the previous tutorials, this structure is similar to that and you will understand this very easily. But let's move on with the pseudocode now. Okay, so now let's go ahead and again take the three different scenarios, that is deletion of a leaf node, deletion of a node with a single child, and deletion of a node with two children. So we'll start with deletion of a leaf node. So let's say you want to delete a node who has the value of 10. So we want to delete this node n4, okay? So you can see we don't have anything to the left and right of n4, so it will have null in it. Programmatically speaking, the value inside the left and right pointer for this leaf node n4 is going to be null, okay? And you want to delete this n4. But this time let's see how the pseudocode will proceed, and we will go step by step in this pseudocode. Now talking about the pseudocode, the name of this function is delete node. It has a return type of tree node star, so tree node is nothing but the class that we've written in C++, and star represents that it will be a pointer basically. So this delete node will return a pointer back, and you'll see why that happens. The arguments that this delete node function takes is another tree node pointer r and the value that is supposed to be deleted. So now as I mentioned, we want to delete a node with the value 10. So we'll call this delete node function, and let's see the first function call. Okay, so this is how the first function would look like. Delete node. We will obviously start with the root node, n1 is the root, correct? So we say delete node n1, we'll pass n1, and the value that we want to delete is 67. So let's assume we want to delete 67 and not 10, my bad. But 67 is also a leaf node, you can see. It is the value inside n6, correct? Alright. Now let's go ahead inside this function. So step number 1, we check if r equals to null. So r value that we've passed in this delete node function is n1. So r is equal to n1, and the value int v that we want to delete that we've passed is v equals to 67. Alright. So when you check if r equals to null, r is not null because r is having n1. So the first condition becomes false. Then you go and check the second condition. In second condition, we check if the value that is supposed to be deleted, which is 67, is it less than r of value. R, as I mentioned, is n1. So n1 slash value is what? What is n1's value? It is 30. So the value supposed to be deleted is 67. So let me replace it over here. Is 67 less than 30? No. So in that case, again, step 2 will not be executed. We will go to step 3. In step 3, we are checking the value if V, that is 67, is greater than R of value. R is n1, n1's value is 30. Is 67 greater than 30? Yes. Now in that case, we will go inside this else if and we will execute 3.1. Now 3.1 says R of right is equal to delete node R of right and the same value V. So what is this line? Over here we are giving a recursive call and we are calling delete node on the right child of n1 because R is n1, and when I say R of right, it would be the right side of n1, which is hash 99, which is nothing but the address of n3. So a second delete node function is called. It is a recursive call. This time we are passing n3 and V is going to be as it is. The value is to be deleted is 67 only, and this is to the RHS. So R of right, let's write R of right over here is equal to, and then we are giving this delete node function call, because you can see this delete node has a return type of tree node star, which means that it is going to return a node pointer and that will be stored in the right address of n1, correct? So R of right is nothing but n1's right. So let's write n1 only over here so that we don't make any confusions. So n1's right is equal to this delete node function. So when this delete node function call is given, the first delete node will go in a pause state. So let's write pause symbol over here, and it is going in a pause state at step number 3.1. And now this second delete node is going to be called with the values of R of right, which is n3, and the value to be deleted is 67. Okay, so as you can see, this is the function call happening. So from first delete node operation, you're calling second delete node, you're passing n3 and 67. The first delete node is going in a pause state at 3.1, and now we will start with the execution of this second delete node operation. So I hope things are clear so far, and I hope you're understanding how the delete node recursive function is being called right now. And now let's start with the execution of this delete node operation again, and this time the R value is going to be n3 and the V value that is supposed to be deleted is going to be as it is 67. So again we'll check if R equals to null. No, R is not null, so first condition will not be executed. We'll check the second condition. If V, that is 67, is it less than R of value? R this time is n3, that is this node. What is the value inside n3? It is 45. Is 67 less than 45? No. So again the second condition will not be executed. Then we'll proceed to the third condition. Over here we are checking else if V, that is 67, is greater than R of value. R of value we just said is 45. Is 67 greater than 45? Yes. So in that case, again step number 3.1 will be executed. We will say R of right. R this time is n3. So n3 of right is equal to, you can see R of right means n3 of right is equal to, again a delete node call. So again a recursive call, and we are saying R of right this time. So what is there to the right of n3? You can see it is hash 43, and hash 43 is the address of n6. So you are passing n6 over here, and the V value, which is 67, is passed as it is. And now again this second delete node function will go in a pause state at step number 3.1, where you are saying n3 of right, which is equal to that new delete node function. And a third delete node function will be called from this second delete node function, and you are passing n6 over here and the value 67. So far what we've been doing is we are just traversing the binary search tree till we find the match, right? Because we want to delete 67. We did not find 67 in n1, and 67 is greater than n1, so we have to traverse to the right. So we came to n3. We again compared 67 with 45, and 67 is greater, so we have to again go to the right. So now we've called a third delete node function, we've passed n6, and now we will check with the n6 value. Okay. So now let's start with the execution of delete node operation again. This time the R is equal to n6 and the V value is 67 only. So again we'll check if R equals to null. No, R is n6. So first step not true. Second condition is also not going to be true. Is V, that is value 67, less than r of value. R is n6, n6 value is 67. Is 67 less than 67? No. 67 is equal to 67, it is not less, correct? So the second condition is false. So you'll proceed to third condition. In third condition we are checking is 67 greater than 67. So again this condition is also now false. So now we are left out with only one last option, which is the else part, and in else part we are checking if the value matches. So this else part will only execute when the value inside the node is going to match with the value that is supposed to be deleted, correct? So inside this again we have some checks, because now we have to find whether that node is a leaf node, or it is a node with a single child, or it is a node with two children, correct? So basically the first three steps were for the traversal till we reach that node to be deleted, and when we reach that node to be deleted, now we have to find whether that node is a leaf node, whether that node has a single child or it has a two children, correct? Okay, so inside the step 4 we have 4.1. So we check if r of left is equal to null. Now r is n6. The left address of n6 is going to be null, and the right address is also null because it is a leaf node, we can see over here. So r of left, which is n6 of left, is equal to null. So this 4.1 condition is going to be true, correct? So in that case what we do, we create a temporary variable. We say temp equals to r of right. So we create a temporary variable temp equals to r of right. What is r of right? R is n6. What is there to the right of n6? We have null. So we will store null in this temporary variable. Okay. Then we will say delete r. R is n6. We want to delete n6. So now I will completely erase n6. Okay. I've erased n6. And now at step number 4.1.3, I'm saying return temp. Temp we just said is having a value of null, and we are saying return temp. When we say return temp, this statement will stop the functioning of this third delete node and it will be returned back to the calling function. So that's how function calls work, right? So when you use the return statement, the function will stop working and return the value which is supposed to be returned to the calling function. Who called this third delete node? It was called by second delete node. So you will go back and a return operation will be done. And when you return this temp equals to null, this null will be stored as the right of n3, because you can see the second delete node was paused at step number 3.1. That's why we've written 3.1 over here. 3.1 is this step in the pseudocode, which is r of right. So r inside the second delete node is n3. So n3 is right equals to this third delete node function, and this third delete node function has come back now and it has come back with a null value, correct? So you can see temp equals to null was returned. So this null value now will be stored as r of right, which is n3 of right. So you can see n3 currently has hash 43. So that will be now replaced with null, because of course you can see we have deleted n6. So now we will have null in it. And now you can see that this link has been broken, correct? And this second delete node function will resume operation after 3.1. It was paused because the third delete node was called. The third delete node came back to second delete node. The second delete node will now resume its operation after 3.1. After 3.1, you can see that we cannot execute 4 because else if got executed. Remember, in a if, else if and else block, only one out of the 3 different conditions will be executed. So if step 1 is executed, step 2 will not be executed, step 3 will not be executed, step 4 will not be executed. That's how if, else if and else works, right? Only one out of the different conditions will be executed. So since the third else if got executed, that is this part, this fourth entire else block will not be executed over here till over here, correct? So after 3 and 3.1, we will directly jump to the last statement in the pseudocode, which is return r. So what is r in this second delete node operation? It is n3. So n3 will now be returned back, correct, from second delete node to the calling function. And who called the second delete node? It was called by the first delete node. So you'll return back n3, that is n3's address basically. And when you do that, the first delete node operation will now resume its operation from step number 3.1. So step number 3.1 in the pseudocode is this step. So when this second delete node will return with n3's address, what is n3's address? It is hash 99, correct? So hash 99 will be returned to the first delete node function call, and it will be stored as n1's write, because you can see at step number 3.1, r of write for the first delete node operation is n1's write, and the second delete node operation is on the RHS, and it has come back with hash 99, and that hash 99 will be stored as n1's write. So n1's write already has hash 99, so it will simply be overwritten over here, and this link will always be maintained. We are not deleting or tampering this link, so this has to be as it is. So that's why this return r is important, to return the original address of n3 back again. And now the first delete node operation will resume its operation after step 3.1. After step 3.1, you'll not execute step 4. As I mentioned, only one out of the if, else if and else will be executed, and since step 3 was executed, step 4 will not be executed. We will directly go to step 5, which is return r, and r at this step is nothing but n1's address will be returned back to the main function. So this first delete node operation was called in the main function, remember that. So when it completes its execution, it will return back n1's address in the main function. So this was the delete operation for a node which is a leaf node, and this is how the 3 different function calls are made. The recursion happens, and that particular node n6 was deleted by following these proper pseudocode steps. So I hope you now understand how delete node pseudocode works. So this is pretty much going to be converted into C++ code, and I hope it was understandable. And now let's see how you can delete a node with a single child. Okay, so now let's say you want to delete a node with the value of 18. So that is n2, and n2 is a node with a single child. So now let's apply this pseudocode again and perform the delete node operation. Okay, so this is how the first function call would look like. You'll say delete node. You'll pass n1 because n1 is the root node, correct? You'll start with the root and you'll pass the value to be deleted. Okay, let's start with the first step in the pseudocode. We'll check if r equals to null. R is equal to n1 and the value v is equal to 18. R is not null because r is n1. So this step will not be executed. You will proceed forward. Over here we will check else if v is less than r of value. V is 18. Is 18 less than r of value? R is n1. n1's value is 30. Is 18 less than 30? Yes. So now this second else if has become true. You will go inside. You will execute step 2.1. Now you will say r of left equals to delete node r of left comma v. So r of left is on the LHS. Let's write r of left and not r of left. Actually r is nothing but n1, right? So let's write n1 of left equals to, and what is r of left? That is n1's of left. You're calling another delete node function call. So this is a recursive call and you're passing r of left. R is n1, who's there to the left of n1? It is hash 16, which is the address of n2. So you're passing n2 comma v you're passing as it is, that is the value to be deleted, which is 18. So when this happens, when you execute step 2.1 in the first delete node operation, a second delete node is called. So the first delete node operation goes in a pause state, and it goes in a pause state at step number 3.1, and a second delete node is called where you've passed the value of n2 as the node value and the value 18 to be deleted. Okay, alright. Now since the first delete node is paused at step number 3.1, let's start with the execution of the second delete node function. Now the r value in the second delete node is n2. The v value is equal to 18. Let's begin with step 1. We are checking if r equals to null. R is not null. R is n2. So this step will not be executed. You will go to second else if. We'll check if v, which is 18, is less than r of value. R is n2. The value inside n2 is 18. Is 18 less than 18? No. It is equal to 18 but not less. So this else if will not be executed. You will proceed forward. Again you will check if this 18 is greater than r of value. Is 18 greater than 18? No. So this means now we have to go in the else part. And when you go inside the else part, remember you have basically found the matching node to be deleted. Okay. Now inside this, as I mentioned, we have to still figure out whether this node has a child, has two children, or is a leaf node. So that's why we have again more if and else if conditions. So the first thing we check is if r of left is equal to null. Now r is n2. So n2 has a left value. What is that? n2 has a left value of #6, which is the address of n4. So r of left is not null. R of left is n4, correct? So this means this 4.1 will not be executed because r of left is not null. So this entire 4.1 will not be executed. And this means that you have to again proceed ahead with 4.2. And in the comments you can see we have node with only one child. So this checking is happening if there is a right child now. So over here we will check else if r of right is equal to null. And this time r is nothing but n2, correct? What is there to the right of n2? You can see we don't have anything, which means that we will have null over here. So over here this is a match. Now in case if even there was something to the right of n2, we would have gone with step number 4.3, which is there for node with two children. But since the right was null, it means that there is a left child because this was not true, 4.1 was not true, and 4.2 has become true. So we have a left child and we don't have a right child. This means that this node has single child, correct? Okay. So now since r of right is equal to null, which is also equal to this condition, we will go inside 4.2. The first step is we create a temporary pointer. We will say temp equals to r of left. R is n2. R is n2. What is there to the left of n2? It is #6, which is the address of n4. So we say temp equals to n4. Okay. Now we see delete r. So r is nothing but n2. We will completely delete n2. Okay. We've deleted n2. Now we'll go to step number 4.2.3. We say return temp. Temp we just said is n4, which was left to the r value, which was left to the n2's value. That is there inside this temp. We will say return temp. Now when we say return temp, this temp which is holding the address of n4 will now be returned to the calling function. Now who called this second delete node? It was called by first delete node. So this temp which is holding the address of n4 will now be returned, and this n4 will now be assigned as n1's left. So remember, when n4 is returned from the second delete node, it will be assigned as n1's left because the first delete node operation was paused at step number 2.1. This is step number 2.1 where we said r of left. Now r inside the first delete node is n1. So n1's left is equal to this second delete node operation, and this second delete node operation has now returned with the address of n4. So n4's address will now be stored as the left address of n1. So n1 has an address of 16, that is #16. It will now be replaced with the address of n4. What is the address of n4? You can see n4's address is #6. So #6 will now be stored over here, and now you can see that n1 will be linked to n4 with this #6 address, because you can see the link was broken in between and we had to establish the link between n1 and n4, and that has happened because this address was returned from the second delete node back to the first delete node and it was assigned as n1's left. So now this link will now be maintained between n1 and n4 because n4's address is #6 and #6 is now stored as the left of n1. That is what happened over here. Okay. So I hope you understood how this linking is also established now. And after executing this step number 2.1, basically our first delete node operation is now resumed from 2.1. And when that happens, after step 2, we will directly jump to step 5 because step 3 and 4 will not be executed. And step 5 saying return r. What is the r value inside the first delete node? It is n1. So n1's address will be returned to the main function, because programmatically in C++ we will call the delete node in the main function. Okay. Alright. So this was the delete node operation for a node with a single child, and that's how the recursion happened, and the linking was also made, and it was made possible because every delete node operation returns the address of a node which can be linked over here. Okay. Alright. Now let's see the delete node operation for a node with 2 children. Okay, so now let's say you want to delete a node with the value 30. So let's take this node n1 itself with the value 30. This is the one that you want to delete. It is the root node, correct? You can also apply this on n3. n3 also has 2 children, but I have specifically selected n1 because this is where we will have to create or include one more function which we will discuss in a minute. But let's say you want to delete n1. So the first delete node call will look something like this. We will pass n1 as the r value and v value is 30. So this is the node value that we want to delete. So first thing we check if r equals to null. No, r is not null, r is n1. Then move to second condition. This condition will become false because 30 is not less than r of value. R is, as I mentioned, n1. n1's value is 30. 30 is not less than 30. We'll proceed to step 3. 30 is again not greater than 30. I'm proceeding a little faster because by now you should have got a hang of it. We will go inside step 4 because this is the else part remaining. We will check if r of left is equal to null. R is n1. Is the left of n1 which is hash 16 which is pointing to n2 null? No. It is hash 16, so it is having some value. So 4.1 will not be executed. You will go to 4.2. We'll check if r of right is equal to null. So right also has an address of n3. So even this part will not be executed. Now we have determined that this is a node with 2 children. So this is where we will go inside 4.3, which is node with 2 children. Now inside this we will call a minimum value node function. Okay. And we'll talk about this function in a second. And that minimum value node operation we will apply on the right side of n1. Now remember in the algorithm when we were deleting a node with 2 children, there was step number 2a and 2b, and in 2a we were saying that we have to find the minimum value in the right subtree. So this is that function. Okay. So at step number 4.3.1 we are saying temp, let's say temp equals to, and we are calling a minimum value node function. Now what is this minimum value node function? Let's see that. And before we go to that, this first delete node function is paused at 4.3.1. So let's do a pause symbol over here. And it was paused at 4.3.1. It called minimum value node function. So let's see this minimum value node function first. Also you are passing r of right, which is n1's right. So r is n1 and right of n1 is hash 99, which is n3. So you are passing n3 over here in the minimum value node function. So keep that in mind. And the reason why you're passing the right node is because you want to apply or you want to find out the minimum value node in the right subtree for n1. So that is this subtree. So that's why you pass n3's address. Okay. Alright. So now let's see the minimum value node function. So this is the minimum value node function. We have passed n3 as I mentioned. And also do note that the first delete node operation is paused at step number 4.3.1 and it has called the minimum value node function and we have passed n3, right? So this is how the function progression is happening. So now let's see this minimum value node function, how it works. Step 1 says set current equals to node. This node is n3. So current is having the value of n3. Now we use a while loop. We say while current of left is not equal to null, current equals to current of left. Okay. So current we just said is n3. What is there to the left of n3? You can see it is hash 26, which is the address of n5. So the left is not null, right? So n3's left is not null. So you'll go inside this while loop. You'll say current is equal to current of left. Who's there to the left of n3? It is hash 26, which is n5. So now n5 will be assigned into current. And again the while loop will be executed. And again you'll check while current of left is not null. Now current has become n5. So let's erase this. Current has become n5. So when I say current of left, we are looking at left of n5. So at the left of n5 we have null. So now we will check while current of left not null, but current of left has become null. It is null. So this while loop will break and you'll come outside and you'll say return current. Current is n5. So n5 will be returned back from this minimum value node function, and it will be stored inside this temp variable because temp was there on the LHS. So let me just show you in that pseudocode. You can see at step number 4.3.1, temp was there on the LHS and we said equal to minimum value node function. This minimum value node function has come back with the minimum node value as n5. So temp has the value of n5. So n5 will be returned from this function and it will be stored in this temporary variable. Now just by looking at the right subtree for n1, the minimum value inside this subtree is 42 only, right? And the logic applied in the minimum value node function is pretty straightforward, and it states that you have to keep traversing to the left of the tree to find the minimum value. Now in binary search tree, remember, the leftmost node at the very bottom will be the least value, right? Because in binary search tree, remember, the node values are arranged in a specific order and the leftmost value is always the smallest. If you look at this entire binary search tree, you can see the value 10 is the smallest because it is to the left most of the entire binary search tree and it is at the bottom. So that is how this while loop will keep on executing till you traverse to the very extreme left, and when you reach the end of the node, when you reach the leaf node, that value that you found is always going to be the smallest value in that subtree. Okay, so that is the logic used in this minimum value node function, and we've got n5 and it is stored in temp. And when this minimum value node function will return back to the first delete node function, the first delete node function will resume after 4.3.1. So let's go ahead and resume that. So 4.3.1 is over here. We are done with 4.3.1. Now we will proceed to 4.3.2. So let's remove this pause sign. We've got the temp equals to n5 at 4.3.1. So we've got n5 over here. Now we've proceeded to 4.3.2. Now at 4.3.2 we say r of value equals to temp of value. Now in the first delete node function, what is the value of r? It is n1. You can see n1. So n1's value will be equal to temp value. Temp is n5. So n5's value is equal to 42. So 42 will now be stored as n1's value. So now n1's value will be erased and we are going to store 42 over here. So remember, in the algorithm also we were finding the minimum value in the left subtree and we were replacing that value in the node that was supposed to be deleted, correct? So n1 was supposed to be deleted, but we did not delete the node. We deleted the value inside the node and replaced it with n5's value. So the next obvious step is now we have to delete this n5, correct? We have to erase this n5 now, and that happens at step number 4.3. In step number 4.3, what we are saying r of right. So let me just erase this first. We are saying r of right, and r is still n1 only because we are inside the first delete node operation only. So we are saying n1's right equals to, and now we are calling one more delete node operation, but this time we are calling it on the right hand side of n1, that is the right child of n1, which is n3. So r of right is still n3, comma, temp of value. So now the delete node that you want to delete should have a value of 42. So remember, we wanted to delete 30. What we did, we erased the value 30 in n1. We got 42, which was n5's value, and we copied it in n1. So the next obvious step is now we want to delete this node n5. So we will call delete node operation, and this time the value that we will pass is temp of value. Remember, temp is nothing but n5. So n5's value is 42. So I hope you're getting what we're doing now. Now we will call a delete node function, recursive function, from the first delete node, because even though we deleted the value 30 from the n1, we have duplicate copy over here in n5, which is 42. So 42 and 42 is now duplicated. So n5 has to be deleted now. So now at step number 4.3.3, the first delete node operation will go in a pause state at 4.3.3, where you are saying n1's right. So r of right is n1's right, and you're calling a delete node function, and you're passing r of right, which is #99, because n1's right is #99, which is n3. So you're calling a delete node with n3 and the value that you want to delete is now 42. So this first delete node operation just gave a call to another delete node. We are passing n3 and the value to be deleted now is 40. Okay? Alright, so I hope you understood what is happening so far. The first delete node is again in pause state at 4.3.3. So now let's go ahead and execute this third function call, which is delete node operation. Okay, so when you begin with the execution of this third delete node operation, the R value is n3 and the V value that is supposed to be deleted is n5's value, which is 42. Correct? So first step, check if R equals to null. R is not null, R is n3. This won't be executed. Now check if V, that is 42, is less than R of value. R, as I mentioned, is n3. n3's value is 45. 42 is less than 45, so we will go inside this. And at step number 2.1, we are saying R of left. So let's write R of left. R is nothing but n3. So n3 of left equal to, we are calling one more delete node because now we have to traverse to the left of n3 because n5 is supposed to be deleted, not n3. So you'll have to traverse over there, right? So this is something which is exactly same that we did for deleting a node for a single child or for a leaf node. The traversal is happening now. So this third delete node will go in a pause state at step number 2.1 and a fourth delete node will be called. You can see over here, we will say n3 of left, that is R of left, and a delete node function call. So R of left is expecting a pointer value, a node value, which will be returned from this fourth delete node. So now this third delete node is in pause state. Let's start with the execution of this fourth delete node function. So when we begin with the execution of this fourth delete node function, the R is equal to n5. The value to be deleted is 42. So step 1, check if R is equal to null. No, R is not null. Check if V value, which is 42, is it less than R of value? R is n5. n5's value is also 42. Is 42 less than 42? No. Step 3, V should be greater than R of value. Is 42 greater than 42? No. So now we will go inside step 4 and we have determined that the node to be deleted is n5. Hence we are going in the else part. And now we have to determine whether this is a leaf node or not. Or it is a node with a single child or double child. Correct? So in step 4.1 we check if R of left equals to null. R is n5. What is there to the left of n5? We have null. So now this condition is true. So we can clearly state that this node is a node which is a leaf node or it is a single child. And when it is a leaf node or a single child, we go inside 4.1, we say temp. So we'll create temp equals to R of right. What is there to the right of n5? It is null only. So you'll assign null inside this temporary pointer. You'll delete R. So you'll completely delete n5. Okay? Because R is n5. Okay? Remember that R is n5 right now. So you've deleted n5 and at step number 4.1.3 you'll say return temp. Temp has null. So when you say return temp, it will be returned from this fourth delete node function to the calling function. And who had called this delete node? It was called by the third delete node. So you'll go back and you'll return temp. So null will be returned. Now this null will be stored as n3 of left. Because remember the third delete node was paused at 2.1. This step where we were saying R of left and R was n3 inside the third delete node. So when this fourth delete node will return with the null value, it will be at the right hand side, RHS. So this null will be stored as R of left, which is n3 of left. So now n3, you can see, had the address of #26 as the left address. So that will be erased and replaced with null. Because of course we have deleted n5, right? So now it will have null. And then you can see that this link is broken now. Okay? And we have successfully deleted that node. Also this third delete node has resumed its operation from step number 2.1. That is after 2.1. And after 2.1 we will directly jump to step 5 because 3, 4 will not be executed because this else if got executed. So over here we are saying return R. R is nothing but n3. So n3's address will be returned to the calling function. Who had called this third delete node? It was called by the first delete node. So you'll go back and you'll go back with n3's address. What is address of n3? It is hash 99. That will be returned and it will be stored as n1's write. So you can see the first delete node was paused at step number 4.3.3. So 4.3.3 is this step where we are saying r of write. So for first delete node, r was n1. So you are saying n1 of write equals to delete node, and this delete node has returned with the address of n3. n3's address is hash 99. So n1's write is going to be equal to n3 only. If you observe the node n1, the write is hash 99 only. So hash 99 will be overwritten over here. Hash 99 will be again overwritten, and this link will be maintained. So we don't have to mess with this linking, right? So that is why n3's address is returned as it is, and n1's write will now have hash 99 only. And once 4.3.3 is done, you'll proceed with step 5, which is return r. R is going to be n1 inside the first delete node. The first delete node will resume its operation from 4.3.3, that is after 4.3.3. You'll go to step 5 and n1's address will be returned to the main function, because this was the very first delete node call. Okay, so this was the little complicated steps when it comes to deleting a node which has two children. And the complication was we had to call this extra minimum value node function, which got us the minimum node in the right subtree, and then you have to replace the value and then delete that particular node. So I hope you've understood the entire pseudocode of the delete node operation for a leaf node, for a node with single child, as well as a node with two children. This is the pseudocode. You can take a screenshot, you can note it down. I'll be sharing the entire code as well as some theory related to binary search tree, so you can find that in the link in the video description. And now the last thing that we have left is we have to convert this pseudocode and the minimum value function node pseudocode into a C++ program. So let's jump to the C++ IDE and directly see the program. Okay, so as you can see, I've opened up my Dev C++ IDE and I've opened up our bst.cpp program. We've been typing a lot of code in this binary search tree program since many tutorials, and in every tutorial we were covering one operation. So far we've done insertion, we've done printing, we've done traversal, we've done the BFS traversal, we've done the search, the iterative as well as the recursive search, we've calculated the height of the tree and whatnot. So only thing left is now the delete operation. So inside the BST class over here, this is where we will perform the deletion operation. I'm not going to explain this entire code right from the beginning because we've already done that previously when we started with the implementation. And of course, don't worry, I'm going to be sharing this entire code with you guys. So you can find the link in the video description for this entire code of implementation of binary search tree and all its operations. So talking about the minimum value order function, this is how it looks like. You can see the pseudocode on the right hand side also. It is taking a node. We are setting the current pointer, which is the type of tree node, to this particular node. Now this tree node is nothing but our own user defined class, which has integer value and two tree node pointers itself, which is the left and right child pointers. Again, I have already created this when we started off with the implementation. So do check out the previous tutorials. And in the while loop, we check if current of left is not null, then you'll set the current of left as the current value, and you'll keep on progressing till you find or till you reach the leaf node, which is to the leftmost of that subtree, and then you'll return that node. Okay, and that will give you the minimum value node. And then below this is where we will call the delete function. Okay, so I've pasted the entire delete function because I don't want to waste time typing the function. You can see the pseudocode on the right hand side and you can compare it with our function. This is the step 1, this is step 2, this is step 3, and then this is the entire step 4, which is the else part. Inside step 4 we have step 4, 4.1, 4.2, and 4.3 is for two children, and lastly we have step 5, we have return r. I'm gonna be sharing this code. You can pause the screen if you want to type out the code. I highly recommend that you type the code once at least. You can easily convert the pseudocode into code also. It is pretty much almost syntactically correct. Okay. Now coming down into the main function is where we are calling the delete operation, right? So you can see we are giving a menu driven program and delete operation is the third option. So case 3 is for deletion, you can see over here. So what we'll do is below this, hit enter, and you'll ask the user to enter the value of the tree node to be deleted in the binary search tree. You'll take that value from the user val. So this val is nothing but a variable that we've created on the top over here. It is an integer value to be deleted. Okay. Then you'll say new node. This new node is nothing but a pointer that I've created over here. So tree node star pointer, and it will point to an object. So over here I'm gonna say new node equals to obj.iterative search and val. So first thing what we'll do is we'll first search a node with that value that the user enters, and if it does not exist, then you'll say that the value does not exist in the binary search tree that you're trying to delete. Enter some other value, right? So then you can use if else. You'll say if this new node is not null, that means if you find a particular value, then you'll say obj.delete node. This obj is nothing but the object of binary search tree class, and you're saying obj.delete node. You're passing the root value because you'll start the traversal from the root, and the val value which is entered by the user, which is supposed to be deleted. And then you can simply say value deleted because that will ultimately delete the value. And in the else part, if this iterative search will return null, the else part will be executed. You can say value not found. Pretty basic. Let's save this. Let's go to execute, compile and run. So our program seems to be working fine. So let's try to recreate this tree by inserting these tree values. So for insertion option 1, we've already covered the insertion operation in previous tutorials. So I enter the value 30. So that would be the root node. So you can see value inserted as root node. Again, option 1 for insertion, I'll enter 18. Option 1 for insertion, I'll enter 45. Option 1 for insertion, I'll insert 10. Option 1 42. Option 1 67. Now if I click on option 4, it will print all the values. You can see printing is done in 2D. So you have 30 as the root node, then 18 and 45 as the children. And for 18 we have the left child, for 45 we have 42 and 67. And I'm also printing the level order BFS traversal which we did in the previous tutorial. Ignore this one. Now what we want to do is we want to perform deletion. So let's delete a node which is a leaf node. Let's delete 10. So for deletion you can see we have option 3. I'm gonna hit option 3 over here, hit enter. Now it is asking the value to be deleted. I'm gonna hit some random value 11. And when I hit enter, you can see value not found because 11 was not there in the tree, right? This is the tree and 11 is not there. So now let's enter again option 3 for deletion. Hit enter. Again it is asking a value to be deleted. Let's enter 10 now and we should get the value deleted as the output. Hit enter and there you go, you can see value deleted. So now if I again print the values, option 4 for printing, I cannot see this 10 over here as the child of 18. So let's insert that again with option 1 and 10. Again printing with option 4. I've got 10 back again. Okay. Now let's delete a node 18 which is a node with a single child. So option 3 for delete. Let's enter 18. Now when I delete this 18, this should be erased but 30 should be directly connected to 10, right? So when I hit enter, you can see value deleted, and when I now print back, you can see this 30 is directly connected to 10. So this program is working pretty good. The only last condition left is to delete a node with 2 children, and again option 3, and we will delete this 30 node which is the root node. So I'm gonna hit 30, and according to our minimum value function, the minimum value node in the right subtree of 30 is 42. So 42 should take this place, right? And 42 should be erased from this place. So when I hit 30 to be deleted, and now when I print the value, I should get 42 as the root node. So when I hit option 4 for printing, there you go, you can see I'm getting 42 as the root node and 42 is deleted from this place. So this means our program is working perfectly fine. We have successfully implemented the delete node operation in a binary search tree. We saw the entire algorithm. We dry run that algorithm onto our visual diagram. We saw the pseudocode. We also dry run that pseudocode with the proper recursive steps onto our visual diagram. And lastly, we converted the pseudocode into C++ program. I know I copy pasted the code, but you should have got the hang of it. If you understood the pseudocode, the program is pretty basic. And of course, I'm going to be sharing the code also with you guys, so you can go and check it out. Do type that code at least once with your own hands for the best practice. And we have successfully implemented the delete node operation. Okay, so I'm gonna wrap up this video over here. I know it was very lengthy, but delete node operation is not straightforward as I mentioned earlier. If you like this video, please give it a thumbs up. Let me know in the comments how this video was. Do share it with your friends. It took a lot of efforts to make this video. It took multiple tries with a lot of editing work as well. So a like and a comment is highly appreciated from your end. So thanks for watching. See you in the next one. Peace.